As of now, we have discussed about decoder, and we developed different kind of decoders of different orders with enable and without enable circuit. But the similar decoder circuit can also be utilized to implement different combinational circuit. So any of the combinational circuit which we have already studied, those all can be utilized to design with the help of decoder circuit. So let us assume the problem is implement full adder circuit using decoder in the OR gates. Okay, so this is this is what the problem is. Now we know that suppose if I want to design the full adder, I can have two things. One will be the sum and the second will be the carry. This is what we know. Okay, we already know these things. Okay, sum and carry is known to us. Now let us see how it can be designed. Before designing, let me explain few things which are required over here. I just told you if we have an OR gate, okay, so OR gate can be represented something like this. See here, I need at least 4 input OR gate over here, okay, because I have the 4 minterms that I need to OR. Here I need 4 input, so 4 input OR gate is required. So there are some other alternative symbol for the OR gate as well. Suppose I have a OR gate which looks like this one and having certain inputs. Okay, let us assume I have a inputs A, B, C, and D, and here are some output. Let us assume I have OR gate something like this. So this OR gate can be represented like this as well. Okay. Okay, and here A, B, C, and D. So this is an alternative representation of the OR gate, something like this. Now let me take another example that so that you will be clear, that your doubt will be clear. Let us assume I have a 4 input OR gate, okay, and having something like, yeah, let us consider 3 input for the simplicity. Let us assume I have a B bar and C, okay, if this is the input, and I want to make the alternative representation for this one. So how I can make it? To make this one, I can have one OR gate, 3 inputs A, B, and C, and only those will be bubbled which are high. Okay, means the B is not connected. So A, B, B bar, and this is C. And if it is not bubbled, what it means, the B bar is at logic low. Okay, so only these are connected, something like this. So this is how you can represent it. Okay, so considering this thing in our mind, let's try to design the full adder circuit with the help of decoder and the OR gate. Here I have a 3 inputs X, Y, and Z. Okay, B bar, because see, if any function is there, some function is there like A plus B bar plus C. So how you will represent this one? To represent this one, you have to write like this. When we are not bubbling, it means it is B bar. Yes, bubbling means C. Bubble means whatever I'm just making over here. This means I'm connecting A to this line. Okay, so this is connected, and not bubbled, not bubbled means this is the complementary. Okay, so the B bar means not bubbled, and A means the bubbled. So the true one will be bubbled, and the complementary will be not bubbled. Okay, so if your function is something like this, so you can represent like this one. Yeah, B bar is just to see here, even though it means it is not connected. Just I'm just showing you this line is indicating B bar. That's it. So A, yeah, the question is like, yeah, the questions are good. Jayant is asking like, if the bubbles are here, okay, then it indicates the true value. And if there is no bubble at this point, so this indicates non-true value or complementary. So this is how we can do that. B bar means simply this line is B bar, that is why it is not connected. So this is just to understand yourself. Okay, it's not a problem. Doubt is clear or no? I don't know. Zayan? Okay, fine. So this is how we can do that. So now let us try to make the full adder, because we need two things. One is the sum and the second one will be the carry. And for sum, this D1, yeah, D1 should be bubbled, D2 should be bubbled, D4 should be bubbled, and D7 should be bubbled. Okay, so 1, 2, 4, 7 should be bubbled for the sum, and 3, 5, 6, and 7 should be bubbled for the carry. Okay, so let us try to see here. If I want to make the sum, I have bubbled D0, D2, D4, and D7, and this is what we will get the sum. Similarly, if I have to get the carry, in that case, I can bubble the 3, 5, 6, and 7, and then you will get the carry. And this is the simple circuit for the full adder with the help of decoder and the OR gate. Okay, so now if you can recall, if you have the IC for the decoder, just by using two AND gates you can make this. Okay, so this is the possibility. This bubble means, yeah, so let me make a simple circuit to make you understand. Like, let us assume I have let me make the bigger part. Let me assume I have this decoder having x, y, and z, x, y, and z, and I have 18 outputs, 1, 2, 3, 4, 5, 6, 7, 8 outputs. And if I want to make the sum, okay, if I want to make the sum, then how it will be? Okay, so what I need to do? I need to simply, yeah, let me write it properly. If I want to make sum, then D1, yeah, here is the D1, D2, D4, and D7. Yeah, this is the equivalent circuit for the sum. Okay, so this is how it will be connected. Rest other will not be connected over here. And this is the meaning of this bubble. Okay, bubble means that line will be considered in the ORI. Okay, so this is the meaning of this one. Hope the doubts are clear. Okay.
Sir, the decoder output indicates the minterms. That's why we are just adding them using all.
Decoder, yeah. So see here, what will ORI means what? ORI means even though if this D0, so what we are doing here, we are just based on these minterms like D1, D2, D4, and D7, we are just making it, we are ORing it, and we will get the sum out of it. So even any one of these, like D1, D2, D4, this is high, then you will get the sum high. Okay, so the sum will be high if any one of these one is high. Okay, you
So
got the point?
D0, D1, D2 are the minterms, no? M0, M1.
Yeah, these all are the minterms. Like, we will consider all these as a minterm. D0 to D7, all are the minterms. And which of the minterm I have to consider, this is based on where you are connecting. Like, because see, for some you need 1, 2, 4, and 7. So here I have connected 1, 2, 4, and 7. Okay, similarly for the carry, you need to connect the minterm like 3, 5, 6, and 7. So all these are the minterms. Yeah, D0, D1, D2, D3, D4, D5, D6, and D7, these all are the minterms. Yeah, so one more question is on the chat. What is that? Sir, also here we have choose E to be 0. Yes, because it is the active low. So what I need to connect, this E must be connected to grounded. Okay, so E must be grounded so that you can get it. Doubt is clear? Arpit, your doubt is clear now?
Yes, sir.
Okay, perfect. So this was the thing. Uh, do we have time? I think the test was for 1 hour, right? Mid-semester exam was for 1 hour, right? What was the schedule? I don't know. Can anyone confirm? I think it was from, no, but we need to check whether the LMS team is ready for that or not. Okay, so let me ask those people, and then we can extend for 30 more minutes. Okay, so that we can cover few things.
Yes, sir. In the schedule, it is given for 10 to 11.
Yeah, that is why I'm asking, because maybe there are some other things, those who are waiting for that, right? Okay, so many people have extended the time duration. So let me inform them. Okay, then I'm extending so that that will be better. Okay. Okay, so we can continue this thing for 30 more minutes. Okay, fine. So I think the doubts are clear here, right? So we can take our classes up to 11:30. Fine. Now let us consider one more example. Suppose I have a function that has been given like x, y, z, and this is given in the POS form. Okay, so this has been given in POS form. So let us see how we can design this circuit with the help of uh, decoder and the NOR gate. Okay, if you see here, the function is given in the POS form. Okay, if it is in the POS form, what it means? We know that the POS form and the SOP form are the complementary in nature. Okay, so suppose any function is given something like this: f x y z, and that is equal to phi m 0 1 3 5 and 7. So this function is nothing but this is same as small f x y z, and that is equal to summation of m and 2 4 6. Okay, so these two are the same. Okay, so if I will make some k map on this, so I need to make these terms as a 0 and rest term will be 0, rest term will be 1. And if I say it opposite, all the terms which I am making it 1, yes, simply just like this. So you can consider like this equation is same as this one. Okay, these both have the same meaning. Okay, so this is what we can do it. Now if we know that whatever the function you have, you will get something like these min terms are at these max terms are 0 and all other max terms are 1. And what this expression says? This expression says that these min terms are 1 and all other min terms are 0, and the meaning of these two functions are absolutely correct, absolutely same. There is no change in these two functions. Okay, these both the functions are same. Okay, now if I want to find the complement of these two functions, then what we can do that? What will be the complement of these two functions? Okay, so if we try to find the complement of the functions, like if I want to find the complement of this one f dash, okay, so what will the complement of this one? That will be like f dash capital M considering the capital F, that indicates the POS form. So X, Y, Z is there. Then we can say that the complement of this function is nothing but this is the summation of M 0, 1, 2, 0, 1, 3, 5, and 7. So this is the complement of this one. So what I am complementing? This one. Okay. So we can also write the F, capital F can be written as this one in the complementary form. Similarly, this function can be written in the complementary form, something like F dash X, Y, Z can be written as like in opposite sense, like pi of M, that will be 2, 4, and 6. So these all are the complementary in nature, and that this is possible. So why I am doing like this? Okay, so to under, yeah, these two are the identical one, these two are also identical one. Okay, and yeah, let me change the color so that will help you. This one and this one are same. Okay, these two are the same. This one is the complementary of this one. Okay, and this one is the complementary of this one. Okay, so this is how you can find the complement, because you need NOR one. So the NOR required the complementary kind of thing. Okay, NOR required complementary kind of thing, and if you are considering the like so you need to write in terms of the min terms. Okay, so the min term is required, and because you are considering not plus R, so if you let me go back to the previous slide, what we did here, whatever the function was there, what was the min term like SOP form was there, what we did, we simply OR all the inputs whatever we had. Okay, so we just OR 1, 2, 4, and 7 to get the sum. Okay, but now because we can OR it, so OR is possible, and because I have to design the circuit based with the help of NOR, so I need NOR gate over here, and if I need NOR gate, I need the complementary nature function, not the direct function. I need at least complement, so I need F bar, and I also need the SOP form. So this equation is the valid that can be utilized to design the circuit. Okay, this is the valid, this equation. Like, see, all these are fine, all these are possible. Okay, but because we are utilizing the, if I used to use OR gate, then this function is sufficient. This is sufficient for if I'm considering the OR gate. But if I'm considering the NOR gate, I need to check the complement of it. Okay, so the complementary nature function I need to check. But because I am considering the OR gate, so I need to check SOP form. Okay, so SOP and complement kind of function will be required to implement this function. Okay, so this is the thing that we need to know. Now, if I want to design this one, so yes, of course, I just told you this particular function is sufficient for our requirement. Okay, because the NOR gate is needed, so you can do it like this. How we are deciding the NOR gate and other things, let me tell you again. If not plus or, yes, see, if NOR or NAND is given, in that case I will use complementary. So NOR or NAND, I will use these two things. If OR or AND is given, then I will use these above two things. Okay, so these are possible. Now, if NOR is given, then the first circuit will be required, and NAND is given, then second will be required. Okay, so let me write it properly. For NOR, this equation is needed. For NAND, this equation is needed. For OR, this is needed. No, sorry, I meant for OR you need this one, and for AND you need this one. Okay, so this is the trick that you can utilize, which of the logic is needed for which kind of circuit. Okay, so if NOR is given, then you need this kind of equation, means the complementary and the SOP form. Okay, any doubt on this? Yeah, this is really a little bit tricky, so you should understand what I am teaching. Okay, the same function can be written in the two-way, and the complementary can be written in this way. The simple thing is, if like not or nor or NAND is given, then you need to find the complement of that function. And if OR is given, then you need to find the SOP, and for AND you need to find the POS. That's it. Okay, and you can make the bubble of all those things accordingly.
Excuse me, sir.
Yeah, please.
Sir, can we use maxterms for decoder?
What we can use? Yeah, of course we
Mm,
can use.
max-
Max term is also possible. Yeah, max term is also, yeah, see here. If you are using this one, this is also possible. Okay, but in this case, you need to use NAND gate. You need to use NAND gate. Okay, you can also use this one. So I'm leaving it to you. Just do all this exercise at your home, and for all the input combinations, try to get the sum and product for all these combinations. As of now, uh, I will be designing with the help of this combination, but this is a homework that you try to design the same with the help of this one, with the help of this one, and with the help of this one, and try to check what kind of outputs you are getting. Okay,
Excuse me,
so
sir.
yeah, please.
Sir, but you told that the D0, D1 all are min terms, not max terms.
No, min term means like those are activated. Yeah, min term may be like different. This is not the correct way to say. Min terms means they are high and they are low. And based on that, we are sampling. We are taking those inputs for either ending or for ORing. Okay, so which are connected, those will be there. So I will recommend just do one thing at home. What you have to do, as of now, I will be designing with the help of this one, but the same problem can be extended with the help of NAND, with the help of OR, and with the help of AND. Once you will be ready with all this circuit, and try to check how those functions are working, and your doubt will be absolutely clear. So I will recommend just do some exercise on designing of this function with the help of other options as well. As of now, I will be designing with the help of NOR only, because the NOR is given over here. But I am expecting that you will try to check with other possibilities as well. And once you are ready with that, your doubt will be clear. So please do it just after this lecture only, so that you will be able to understand what is the concept. Okay, so let me try to analyze a few things. Like if here we have three inputs X, Y, Z, and enable, yeah, active low is there, so I need to connect this enable circuit to the grounded. Okay, so this will be connected to the grounded, and if I'm talking about the NOR one, yeah, or this NOR kind of structure, so I need to consider 0, 1, 3, 5, and 7. So 0, 0, 1, 3, 5, and 7 will be there, and I need one NOR gate over here. Okay, so this is how you can design this function. Okay, similarly, suppose if we are designing with the help of the same function, if you are designing with the help of OR, okay, with the help of OR, then what you have to do? You have to simply 2, 4, and 6. So let us assume I have one line over here, and I have used one OR gate. Okay, so if this is the function, so I need to use 2, 4, and 6. So 2 will be bubbled, 4 will be bubbled, and 6 will be bubbled, and you will get the same function. Okay, similarly, if you are using, yeah, let me do it, because see, yeah, let me do it properly. Okay, oh, sorry. Okay, here are some lines. Now let us do one by one. I can have 1, OR gate. If I have a OR gate, and if I want to make the same function with the help of OR gate, then 2, 4, and 6 will be bubbled. 2, 4, 6 will be bubbled. And if you are making the with the help of AND gate, okay, so 0, 1, 3, 5, 7, 0, yeah, the same thing, like 0, 1, 3, 5, and 7. Okay, and similarly you can do for others. Yeah, just try to check it. Like you just have to make the truth table of all these possibilities for this one, for this one, for this one, and the last one. Okay, and if you have all the possibilities, then you can check it out whether they are same or not. Okay, so this is
Sure.
doable. Yeah.
For this situation, when we are putting the input D0, then it should be 0 for max term. And if we did the similar way like
Here
OR,
here
then
somewhere I will get, like if I'm using AND and OR gate, this is in the, yeah, let me do one more thing. This is in the complementary. So see here, let me check the combinations. Like if 0, 0, 0 is there, XYZ is 0, 0, 0. Okay, so this D0 will be 1 and rest all other will be 0, right? 1, 2, 3, 4, 5, 6, 7, 8. Okay, so this is the possibility. If 0, 0, 1 is there, then the possibility will be 0, 1, 0, 0, 0, 0, 0, and 0, and so on. Okay, now if I want to make, like, see what will be the function is like, if we try to see the if you try to simplify it, you just need to simplify this k map, and you need to check what is the function is coming out, right? And accordingly you need to check how you can say, like, see here, either of anyone is sampled here, anyone is sampled here, either 0 or 1, 0, 1, 3, or 5, or 7, that will be odd here, that will be not here. Doubts are clear or not? I don't know. Just simply what you have to do, just do one thing, just complete this table and try to get this function output, okay, based on this connection. Okay, either you can use a SOP or POS, anything you can use, and just try to get this function, and might be your doubt will be clear.
Excuse me, sir.
Yes, please.
Sir, this D not D1 can behave as max term and as well as min term both.
Yeah, because see, based on your sampling, this D0 and D7, D0 to D7 will be decided whether they are min term or max term. See here, let me repeat it again. Suppose the combination is like 0, 1, 0, 0, 0, 0, 0, 0. Okay, if you are sampling this one, okay, if you are sampling this one, so 0 will be sampled. If you are sampling this one, then 1 will be sampled. So what you want to sample, you like what kind of sampling you want to get, accordingly you can make it. Okay, so by the AND gate, what you have done in NOR and NAND, both functions are similar. Okay, and NOR is equal to AND gate. Okay, so you're saying like this, but this is not the case. Saying like this, so one function is complementary. Yeah, one function should be complementary. Like this is the function, so this should be complementary. So let me see it. Let me repeat it again. What is it is done? Okay, so if we see the De Morgan's law says that, like, suppose you have some a and b and some function f, so this can be replaced with the bubbled one. Okay, bubbled AND gate. So if this is the case, then this can be replaced with the bubbled one, and that will be complementary in nature.
yes, sir, we should
No, complement,
not
yeah.
get. Yes,
Yeah,
sir.
not get. Yes, this the function will be complementary in nature. Okay, so two function will be, yeah, because oh sorry, we have already considered these two, right? So two are the same function and two are the complementary in nature. Sorry, we missed these things. Okay, so we already have considered these things. The two are true in nature and two are in the complementary in nature. Okay, so the f bar will be here. Okay, so you need to apply the De Morgan's and that will be done. So here I will get f complement. We have already done it. I think I missed it. Okay. Okay. So f bar will be there and the other one will also be there, f bar. Okay. I try to find the truth table and do all these things. So this is easily doable. You can do it. It's possible. You did not get this complement. Complement, see here. One thing. Let me explain it. If you are considering this, so suppose here what I did, I consider it like not NOR gate is here, right? What I can do, I can replace this NOR gate with the AND gate, with the AND gate. Okay, bubbled with the bubbled one. Bubbled means I'm complementing. Okay, I'm complementing means what are the inputs I have connected? I need to use opposite one. Sorry. What are the input I have connected? I have to use opposite one. So here the opposite one is will be considered. But again, if we are finding the complement of it, so see here, let me make one more line. So might be that will be helpful for you. Okay, now can anyone tell me the first and the last function are same or not? These two are same or not? These two are same, right?
Yes.
Yes,
These
sir.
two are absolutely correct, because see, we know that we have applied the De Morgan's theorem here. If these two are same, okay, then what will happen? If I want to remove this bubble over here, then what I can do? I can simply, whatever the cross I have made, I need to change it. I need to complement it. So if you see here in this case, what I did, I have just, yeah, so I think this is the complementary. So let me, yeah, let me make one more circuit here so that you will know these things, how we have done it. So let us assume one more column here. I have one AND gate only. See, this one and the last one is same. And if I want to only make, I want to remove this inverter, which we have bubble over here. So what I can do, I need to change the functions. So this will be one, this will be one, this will be one. So this is how this is same as this one. And this is the function, whatever you will get. And this is same with this one. Points are clear or not now?
Yes, sir.
And this is same. Okay, so this function is same as this one, and this function is same as last one. Okay, so what I have done, I have just finded the De Morgan's theorem to get this one, and here I am getting the bubbled one. So to remove this bubble, what I have done, I have connected, I have just complemented the bubbles, the connections, whatever I have made. So what the function I am getting here, this one, this is same as this original one. Okay, and if I want to make the complement of it, yeah, might be this is not true. This is not true. Yes, absolutely correct. This f bar is not true, because the bubbled AND gate is not same as the bubble. Yeah, so this is not true. This may be different. Yeah, so here I need to use a different kind of logic. So this may not be true. Okay, so this is not correct yet. Don't consider it. Consider this one. Okay, I think I made some mistake before. Okay, so now I think the points are clear in how you can do that, how you can make it. Okay, any doubt after this?
The first one is also incorrect, I think.
First one, this one. No, this is the same as this one. See here, let me repeat it again. What is there? Whatever the function we got here, This is same as this one. Okay, what we have done, we have just simply applied the De Morgan's law. Okay, and we are getting this one. Now here we have a bubble. To remove this bubble, what we can do, we can simply complement the connections. Okay, whatever the connection we had, just I need to complement it. So here in the last one, I had the connection with D0, D1, D3, D4, and D7. But if I want to make the complement, I just I will get like the connection with D2, D4, and D6 only. And this is what your actual function is. So this is same as this one. So the first, second, and the last one will be the same function. They will give the same function. Okay, yeah, try to do it at home. Like, this is really very interesting, right? So try to find all the possibilities, all the permutation and combination, and then your doubt will be clear.